Okay, let's dive into something pretty revolutionary in the world of artificial intelligence. We're going to unpack some really cool research that argues the secret to smarter AI isn't just about feeding it more data, it's about teaching it to understand cause and effect. So let's kick things off with a bit of a puzzle. Imagine you have this AI, right? It's an absolute genius at spotting cows. You've shown it thousands of pictures, and it nails it every single time. Then, one day, you show it a photo of a cow on a beach, and it looks at you and says, "That's a camel." Why on earth would it make such a wild mistake? And this isn't just some funny thought experiment. It points to a really deep, fundamental flaw in how a lot of AI models actually learn about the world.
Well, the culprit has a name: spurious correlation. You see, the AI didn't actually learn what a cow is, the shape, the spots, the whole deal. Nope, it took a lazy shortcut. It just noticed that in pretty much every photo it was trained on, cows were standing on green grass. So it made a super simple but totally wrong rule. Green background means it must be a cow. The second it saw a cow on a sandy beach, that rule shattered and the whole system just got confused.
And this gets us right to the heart of a massive challenge in AI today. We see these models doing absolutely incredible things, but they can also be, well, surprisingly brittle. They can break in the most unexpected ways the moment the world doesn't look exactly like the textbook they studied from.
The fancy term for this is the out-of-distribution problem, or OD for short. It's like this. You can train a model in one specific environment. Let's say photos of animals in European fields, and it works like a charm. But the minute you test it in a brand new environment, like an American desert or a city street, its performance can just totally fall off a cliff.
Now, people have been trying to crack this nut for a while. Some of the early ideas, like a method called Invariant Risk Minimization, or IRM, were a really great start. They tried to find features that were always stable or invariant, no matter the environment. Brilliant idea, but it really only worked well for simpler, more straightforward problems. When you threw the messy, complicated, nonlinear data of the real world at it, like photos, it just kind of hit a wall.
So if that didn't quite work, what's the answer? Well, this research proposes a really exciting new path. It's an approach that tries to teach AI to think less like a simple pattern matcher and more like a scientist, by getting it to understand the actual causes behind what it's seeing. The method is called Invariant Causal Representation Learning, or as we'll call it, ICARL. And the whole game here is to stop looking for features that are just correlated with a label, and instead hunt for the features that actually cause the label in the first place. So here's the absolute key difference, the big shift in thinking. A traditional AI asks, what stuff is usually around when I see a cow? And it learns, oh, green grass. But iCarl asks a much smarter question. What features are the reason this thing is a cow? And it learns that it's the animal's physical shape. The background? Totally irrelevant. Now, this entire approach is built on a really profound idea. The model basically assumes that out there in the real world, there are these hidden, fundamental properties, these causal factors that are responsible for creating both the thing we see, like the pixels in a picture, and the name we give it, like cow. Okay, so how in the world does iCarl find these true causes? It's not magic, I promise. It's actually a super methodical, three-step discovery process that feels a lot like running a scientific experiment.
All right, here's how it works. First up, it looks at all the data and tries to identify all the potential hidden variables. All the different ingredients that make up an image, like shape, color, texture, you name it. Then, for step 2, it runs a series of really clever statistical tests to figure out which of those ingredients are the actual direct causes of the label. And finally, once it's locked onto the real causal factors, it builds a brand new model that only uses that solid gold information, and it learns to completely ignore all the other spurious, distracting junk. So, the big question, does it actually work? To prove it, the researchers set up a brilliant test using a data set called Colored MNST. It's a standard task of recognizing handwritten digits, but they added a nasty little trick. In the training data, the color of a digit is almost always linked to what number it is. So, for example, maybe all the 2s are red and all the 7s are green. A normal AI is going to fall for that trap for sure. And this just shows you how well iCarl works. After it was trained, the researchers could actually go in and fiddle with the hidden factors the model had learned. And look at this. When they tweaked a factor that iCarl said was causal, it changed the actual shape of the digit. But when they messed with a factor it had flagged as spurious, it only changed the color, leaving the number itself perfectly intact. It successfully pulled apart the cause from the correlation. It's incredible. The results are, well, they're just stunning. They tested it on a new dataset where the color number rules were flipped to try and trick the AI. The standard model completely failed. Its accuracy plummeted to around 22%. But iCarl, because it had learned to ignore the color, it scored nearly 74% accuracy. That's almost the best score theoretically possible on this test. It worked. A success this big points to something more than just a smart new algorithm. It actually suggests a whole new way of looking at AI, a new worldview, really, about how intelligence itself relates to the world around it. And it's called the agnostic hypothesis. The core of it is this: there is a hidden layer to reality, a set of true causal factors that are responsible for creating both the things we see and the names we give them. For years, AI researchers have debated these different views. Does an image of a cat cause us to use the label cat? Or does the abstract idea of cat somehow cause the image? Well, the agnostic hypothesis just steps in and says, what if you're both wrong? It suggests that there's a hidden set of what they call nature variables, the real physical essence of a cat in the world. And that is what causes both the image we see and the label we use to talk about it.
This is such a powerful way to look at things because it could actually unify the entire field of machine learning. Seriously. Whether you're doing supervised learning with labeled data, unsupervised learning with no labels, or even reinforcement learning with an agent taking actions, you can reframe all of it as different ways of tackling the same fundamental quest, trying to discover the hidden, true causal structure of the world.
So, what this all boils down to is a new roadmap for the future. The path to building truly robust general AI might not be just about throwing more data and bigger computers at the problem. It's about designing systems from the ground up that are built to figure out these deep, unchanging properties of the world, these nature variables, from all the messy, correlated stuff they see every day.
And that leaves us with one final, pretty mind-bending question to think about. If we actually succeed, if we build an AI that can look past all the noise and correlation and truly learn the hidden causal machinery of reality, what in the world is it going to teach us about our own universe that we can't currently see for ourselves?